So the second half of our note, we're still talking about cars that are driving in circles, except this time the car isn't driving in a horizontal circle. I mean, the car is still tracing out a horizontal path, but now the car is on a banked turn. So you've probably seen these, especially on highways, coming on highways, getting off highways. You have these banked turns. There's actually a good reason why they exist. So many turns on the road are actually banked at an angle so that cars have to rely less on friction when making the turn. Remember, when the car was making a flat turn, it required entirely on friction in order to make the turn and not slip. Now, if the car is at an angle, some component of the normal force is going to be acting in the direction of the center of the circle. When analyzing problems like this, we have to assume that the car doesn't slip on the incline, so it stays at the same height on the incline as it completes its turn. So if the car starts at this location on the incline, it traces out that exact perfect circular horizontal path all the way around the incline. Otherwise, it's not uniform circular motion. Banking angles are designed, so people actually design these on purpose, so that the car doesn't need to rely on friction at all when making the turn. This means that when you're designing a banked angle, you assume a certain speed, you assume a certain static frictional coefficient between the car's tires and the surface of the road, and then you design the bank, you design the angle of the bank based on that. Obviously, that's not going to be true for every car that goes on this banked curve, but you always, as a designer, choose the necessary speed of the car, and you assume a certain coefficient of friction, and you say, okay, hey, given this speed and this coefficient of static friction, what is the perfect angle of this bank so that a car does not need to rely on friction at all? So we're going to pretend we're designing a road, and we're going to come up with some banked angles so that a car actually doesn't have to rely on friction at all. So let's look at the forces acting on this car as it cruises at the perfect speed for this particular banking angle, and therefore doesn't have to worry about friction. So we're assuming this car is perfect for this particular banking angle. So for this car, the forces acting on it are gravity and the normal force. The normal force is perpendicular to the surface. There's something perpendicular to the surface. Here's something parallel to the force of gravity. This banking angle is theta, which makes this angle theta, and it makes this angle theta. So that means I could break Fn into an x and a y component. I could call this Fny. I could call this Fnx. So the only component that's acting towards the center of the circle right now is Fnx. That is what's allowing the car to travel and follow uniform circular motion. This angle is banked perfectly so that no friction is required to keep the car on the incline. So now what we're going to do is we're going to solve this problem using Newton's second law, and we're going to find the relationship between the critical angle for this banked turn, the speed of the car, and the radius of the circular path. Oh, and also g. I'm just going to turn that over. We'll use the back. Okay, so here's our free body diagram drawn a little bit nicer with just a box. I'll move this down so you can actually see it. We've got Fn. We've got gravity acting straight down. There's our banking angle theta. And just for fun, there's our banking angle theta. Fn has a y component and an x component. We've got an up direction, and we've got a direction towards the center of the circle. Boo, you're in the way again. Okay, now Newton's second law. F net x equals max. In this case, our x direction is radial. So the only force acting in the x direction is Fn in our x direction. And this is equal to m times our centripetal acceleration, which is mv squared over r. In our y direction, F net y equals may. In this case, there's no acceleration up or down. the car is staying at the exact same location on that ramp. So Fny subtract Fg equals 0. Fny is just Fn cos theta. That's equal to mg. So Fn is equal to mg over cos theta. In the x direction, Fn sine theta is equal to mv squared over r. We're just going to sub one thing into the other, and we're going to get mg sine theta over cos theta equals mv squared over r. So we can make a couple of substitutions here. M's will cancel, which means our banking angle does not depend on the mass of the car going past it, which is nice. The other thing we can simplify is this term here. Sine theta over cos theta is just tan theta. Tan theta equals v squared over r times g. And that's it. That's our relationship between the banking angle, the speed of the car, the radius of the turn, and g. Next up, example number 3. At a racetrack, cars travel through a 316-meter radius curve that is banked at 31 degrees. A. At what speed would the race cars be traveling if they wanted to pass through this curve without relying on friction? So, okay, there we go. So, we need to figure out if 31 degrees is the critical angle, what is the speed the car needs to be going at? B. Does this speed depend on the mass of the car? C. If the cars actually travel through this turn at a faster speed, what additional force is necessary? And D. If the cars actually travel through this turn at less than the critical speed, what additional force is necessary? So we're not solving C and D, we're just going to think about it, and we're going to draw a free body diagram. A, I'm going to take a shortcut. We've just derived this relationship. So the relationship between the critical angle theta, the speed of the car, the radius of the track, and g, 9.81, is this. Subbing in our numbers, where we have r is 316 meters, theta is 31 degrees. We're assuming there's no friction, so this is a perfect speed for that critical angle. Our speed ends up being 43.1584 meters per second. 3 significant figures. Therefore, the car would need to travel at 43.2 meters per second so that it doesn't need friction. B was, does this speed depend on the mass of the car? I'm going to go back to our previous analysis where we derived this. Does speed rely on the mass of the car? No, it doesn't. We showed that in our analysis. The speed of the car has no relation to mass. I'm going to write now. C, previous derivation. C, this one we have to kind of think about for a little bit. If the car is actually traveling through this turn faster than 43.2 meters per second, what additional force is necessary? So let's say here's our car. I've got a little floof. Here's our car. It's banked at this angle, 31 degrees. It's still going to be experiencing some normal force. It's still going to be experiencing some force of gravity. That angle's 31 degrees. But now it's going faster than it was before. It's going faster than 43.2 meters per second, which means if it wants to make that same curve with a radius of 316 meters, it requires a larger centripetal force. So more force, an additional force, is needed directed towards the center of the circle to keep that car going in a perfect circle, undergoing uniform circular motion. So that gives us a hint as to something acting in this direction. Another way you could think about it, if the car is traveling faster than the critical speed, it is going to tend to slip up the incline. What prevents it from slipping up the incline? Some friction. In this case, we don't want it to slip up the incline, so we're dealing with static friction. So if the speed is greater than 43.2 meters per second, static friction must act down the incline to prevent the car from slipping up. Next one. Now we're going to draw the free body diagram if the car is traveling at less than 43.2 meters per second. Here's our car, same incline, normal force, that's an N. There's our angle theta, here's our force of gravity. Now the car is not going as fast. So the force, the centripetal force required to keep it going in a circle is less than it was before. So we need to lessen this x component of the normal force. We would lessen it if we had a force in the opposite direction, going up the incline. Another way to think of this, if the car is going slower, it's going to tend to slip down the incline. To prevent it from slipping down the incline, we need some friction up the incline. Again, we don't want it to slip, so we have static friction. So if the velocity, or the speed I should say, is less than 43.2 meters per second, static friction must act up the ramp to prevent the car from slipping down. Okay, that's it. Example number 4, you may not have time to get to in class. It's a little bit trickier than the other examples. If you don't get it done in class, please try it for homework. Come back and take a look at the solution. So here's example number 4. We have a banked turn at the Talladega Speedway. We want to figure out for part A, what is the critical speed so that friction is not required in order to produce the centripetal acceleration. By the way, the most important terms on this summary sheet are the radius of the turn, which is 335 meters. The other important number is, was there a banking? No, I think that's it. B, what is the minimum required static coefficient of friction if cars make this turn at 79 meters per second? And C, what is the minimum required static coefficient if a car only wants to travel through this turn at 6.9 meters per second? So this is actually very similar to our last example, except this time we're throwing in some numbers. So for part A, what is the critical speed so that friction is not required in order to produce the centripetal acceleration? We came up with that relationship a second ago, and it was this. Tan theta equals v squared over g times r. In this case, oh, sorry, there was another, I knew there was another thing here. The angle. Where did I... Oh, okay, I think it didn't print. Have a look on the actual Smart Note. Sorry, guys. The banked angle is actually also given to you in this question. Clearly did not print very well. The radius is 335 meters. I swear there's supposed to be a banked angle there. It's 33 degrees. That makes a little more sense now. Okay, so solving this formula, v equals the square root of tan theta times g times r. We should get a speed required 46.1972 meters per second, and we're dealing with two significant figures. So that is the critical speed so that the car does not need to rely on friction. Now that we know that, we're given two scenarios. One where the car is going fast, faster than this, and the other one where the car is going slower than this, which is just like the examples we looked at in example number 3. So B, what is the minimum required static coefficient of friction if the cars make this turn at 79 meters per second? So in this case, free body diagram. Here's our car with its little wheels. We've got our normal force. Our angle theta is 33 degrees. Here's FG. Now, if the car is going more than 46 meters per second, a static frictional force is required down the ramp to prevent it from slipping up. I'm also going to label this angle here, which is theta, because we are going to need to break some of these vectors into components. Yay, our favorite thing. This is up. This direction here is towards the center of the circle. Okay, let's go ahead and break this down into x and y component. F net x equals max. F net y equals may. This is equal to 0. However, in the x direction, ax is just our centripetal acceleration. In the x direction now, we have two forces with components in the x direction. We have static friction with this x component. This is actually static friction times the cosine of theta, so FSF times cos theta in our positive direction. And we also have this x component of the normal force, which is just Fn sine theta in the positive direction. And this is equal to m times our centripetal acceleration. This is mu s Fn cos theta plus Fn sine theta equals m v squared over r. Over here, we have an upward y component due to the normal force. This is Fn cosine of theta in the positive direction. We have a downward component due to static friction. This is actually static friction times sine of theta, and that is in the negative direction. And of course, we also have gravity acting directly down in the negative direction, and that all sums to 0. So we've got Fn cos theta subtract mu s Fn sine theta equals mg. It looks kind of messy, but actually we've got Fn repeated a whole bunch of times. We don't care what Fn is, so let's rearrange one side for Fn and sub it into the other side. The usual. So I've just factored out Fn from the left-hand side of this equation. Rearranging now. I have this. So let's go ahead and sub in. I'm just gonna do a quick little rearrangement over here as well. It might look a little neater. Now we'll sub in. mg times this term, mu s cos theta plus sine theta equals mv squared over r, and this side is over this term here, which is cos theta subtract mu s sine theta. It's kind of nice when things look neat. We have an m we can cancel out, which is always nice. And then we just need to rearrange a little bit and solve for mu s. So I'm going to factor g, actually not factoring, I'm going to distribute g into the term over here. So I get g times mu s times cos theta plus g sine theta equals, then I'm going to distribute v squared over r into this bracket here because I'll just multiply it on the right side of my equation. I'll get v squared over r cos theta subtract mu s v squared over r sine theta. Now I'll just collect some like terms. Excuse me. Mu s terms I'm going to collect on the left-hand side. At this point, if you're sick of rearranging, go ahead and sub in numbers by all means. So far, so good. I'll factor out mu s. Now, I have an equation for mu s, and I'm just going to sub everything in one step and solve. Boo will help me by walking on things and tilting my entire camera. There we go. This number should end up coming to, drumroll, 0.55957, rounding to two significant figures, is 0.56. What does that tell us? Why? We've been at this for a while. What is it actually telling us? That is the minimum required static coefficient of friction for a car that's traveling at 79 meters per second. So it needs at least that static coefficient between tires and ground if this car traveling at that speed wants to undergo uniform circular motion on this particular track. Okay, last one. Very, very similar process. Definitely try this one on your own and then come back and check the solution. But C is, what is the minimum required static coefficient of friction if a car only wants to travel through this turn at 6.9 meters per second? So back to the side, how far up can I write that you can see? About here. Here's our little car. Go down a bit. Here's our normal force with some angle. Oh, I went too far up again. Here's our force of gravity. In this case, because the car is going so slow, it will tend to want to slide down the ramp, which means we're going to need a force of static friction acting up the ramp. The angle theta applies right there. So that's what our free body diagram looks like. In this case, we've got an upward direction, and same as last time, we've got the center of our circle in this direction. Exact same analysis as before. F net x equals max. F net y equals may. In our x direction, the acceleration is purely due to centripetal acceleration. If you wanted to sketch that in, I often do this, if you wanted to sketch that into your free body diagram as a little squiggly line, just to remind you the acceleration is directed towards the center of the circle, go ahead and do that. I often do that when I'm doing these sorts of free body diagram drawings. In the y direction, the net force is 0. So in the x direction, we have a positive x component due to the normal force, which is the same as before, Fn sine theta. We have a negative component of the static frictional force, so negative static frictional force times cos theta. This is equal to mv squared over r, which is our centripetal force. Here we've got three terms that involve y forces. We've got our y component of Fn, which is Fn cos theta. We've got an upward force due to static friction, plus F static friction times sine theta. And we have our downward, so negative force of gravity, minus Fg equals 0. So Fn cos theta plus mu s Fn sine theta equals mg. So we have something very similar to the last question. In fact, the only difference is a couple of positive and negative signs here and there. So I'll go through and fairly quickly do the same process, rearranging for Fn to start in the y direction, and then doing the same in the x direction. Fn sine theta, subtract mu s Fn cos theta equals m v squared over r. Fn sine theta, subtract mu s cos theta equals mv squared over r. Now we'll just sub in. So we'll get mg times sine theta subtract mu s cos theta. Hi boo, thanks for that. Tail in the face. Over cos theta plus mu s sine theta equals mv squared over. This is actually good. You're getting an idea of what it's like for me to do work at home while I'm marking your tests. There's a cat walking over them. Sorry in advance. So canceling out some m's again, distributing some things. G sine theta subtract mu s g cos theta equals v squared over r cos theta plus mu s v squared over r sine theta. Rearranging some mu s's together. I'm going to put those on the right-hand side this time to mix things up. Mu s v squared over r sine theta. I've got g sine theta over here minus v squared over r cos theta. So it looks very, very, very similar to last time. Plugging all my numbers in at this point, I end up getting 0.629. Oop, there we go, to two significant figures. Therefore, the minimum mu s is 0.63 if this car does not want to slip, wants to travel at uniform circular motion going 6.9 meters per second.